Hi there, this is Richard Walker from Lucidate. Welcome to this third video on ensemble techniques where we will look at boosting. This is a modern AI technique that has evolved from random forests. It is normally described and demonstrated to work with decision trees and forests, as we shall see, but the basic boosting technique is agnostic to the choice of AI algorithm. It can be applied to support vector machines, k-nearest neighbours, neural networks, indeed any machine learning or AI technique. This means that boosting can be used for regression, that is predicting a numerical value, or classification, determining what class a variable belongs to. In this video, we will focus on classification. This video assumes that you're familiar with decision trees and random forests. There are some links in the description if you'd like to refresh your knowledge on both these techniques. This video will talk about classifiers and how bagging reduces classifier correlation and improves performance. We will then introduce boosting as an extension of bagging. Recall that bagging randomizes the dataset to create a set of uncorrelated learners that vote on an outcome. The idea behind boosting is not to introduce a completely randomized dataset, but to produce a dataset that is richer in samples that the classifier struggles to correctly identify. A good analogy here is a sports coach. Sports coaches will spend less time on coaching where their client is already world class. Instead, they will focus on elements where the athlete is weaker, with a greater improvement in overall performance. We'll look at the boosting algorithm and see how it achieves its goal of creating more challenging datasets to get the ensemble of learners working hard on areas where they are weak. And then in the next video, we'll look at some results to compare base decision trees, random forests, and boost-based learners. Classification tasks can be multi-way. Classification of these alphanumeric characters is a 76-way choice, or binary, such as whether a prospective borrower is likely to default or not. We can calculate the error in our classifiers. This will range from 0 error, where all samples are correctly classified, or 1, everything is wrong. If your multi-way classifier has errors over here, then you're dead in the water. If the error is in this region, then you have a useful classifier. Very often, we will have weak classifiers whose error is only a little better than flipping a coin. But, as we've seen, even weak classifiers can be extremely useful if you have enough of them and their errors are uncorrelated. We can let them vote as part of an ensemble. The error of such an ensemble in aggregate results in extremely strong classifiers. One interesting observation for binary classifiers only is that extremely high error rates make for extremely good contrarian predictors. We simply invert the output and get the correct outcome nearly all of the time. Let's describe the key principles behind the boosting technique and then examine the details to see how boosting works in practice. Here we start with a decision tree labelled H1 that has a classification accuracy of 82.3%, meaning that in this sample it gets 82.3% correct and 17.7% of samples are misclassified. Then let's build a second classifier to work as an ensemble with H1. If we use bagging, we can randomly shuffle this dataset and allow duplicates. The decision tree derived from this data will also make mistakes, but crucially it will make different mistakes from H1. If we combine enough of these diverse trees and allow them to vote, then we can get a big uptick in accuracy. But can we do better than simply random shuffling? What if instead we deliberately created a training set that has a higher proportion of data that H1 misclassifies? A learner, H2, created from this dataset will be more sensitive to these misclassified samples from H1 and will be able to cover some of its blind spots. We can then build a third learner from this dataset by shuffling again. Once again, we won't shuffle completely randomly. For our next learner, we will include a higher proportion of training data that's classified differently by H1 and H2. For a binary classification, one learner will be correct and one will be incorrect. We don't really care which, but we would like our third classifier to be able to cast the deciding vote, hence being more sensitive to sample data in which the two prior classifiers disagree will help H3, our third classifier, in its decisive role. We can keep repeating this process as we train more and more models. We're certainly making the process of learning much more challenging by skewing the dataset to include more difficult samples, but this is what ultimately makes our models stronger. Again, this is akin to a sports coach getting athletes to focus on their weaknesses rather than their strengths. Let's describe how the boosting algorithm works with decision trees at a conceptual level, and then to gain a more practical understanding, work through a specific example. As with bagging, a portmanteau of bootstrapping and aggregation, we introduce AdaBoost, an amalgamation of adaptive and boosting. There are three key ideas behind AdaBoost that make it different from other machine learning algorithms, such as random forests. They are, firstly, create a very, very large amount of weak learners. Secondly, give each model a weighted vote based on the strength of their classification. And finally, develop learners in order, with errors in prior models influencing the building of the next learner. So here's some example lone default data, and here is a decision tree made from it. If we choose to build a random forest, then we would make a series of trees with multiple branches and leaves based on our bagged data. But for AdaBoost, we build tiny trees that are made up of a single root node and two leaf nodes. You'll hear these simple nodes referred to as stumps. Secondly, when we build a complete random forest, all of the trees have an equal vote. But for forests of stumps using AdaBoost, each stump gets a weighted vote based on how well it identifies the correct outcome. Finally, when we create trees in a random forest, we can create them in any order, but the order of stump creation matters. Each stump we create is designed to overcome some of the weaknesses in prior stumps. So let's walk through this simple dataset to make these ideas more concrete. We'll build a forest of stumps to predict whether a potential borrower will default or not. For this simplified dataset, we're just going to use three input variables: the rating, the debt to income ratio, and whether this borrower has previously defaulted or not. The first thing we do is give each sample a weight representing the importance that this record is correctly classified. At first, we will assign all of our samples to have the same weight, in this case 1 divided by the total number of samples, which is 12. We will change this value later to give samples that our classifiers get wrong a higher weighting, and you will see how this will skew our training data and force it to include more samples that are more difficult to classify. We then go through our Gini impurity calculation that we introduced when we presented decision trees. If you're unfamiliar with this approach, see the link in the description. What we want to do is to see which of the variables, i.e. the rating, the previous default, and the debt to income ratio, when used on its own in a stump, gives us the best split of the data. The Gini impurity calculation tells us that on this data, the best split is on rating, with the optimum split on a rating of B or above. Having figured out that this is the best stump, we next need to determine how much weight its vote will carry in the final classification. Some stumps will get more say than others based on how well they classify the data. This stump makes just 2 errors. Record 2, which the stump classifies as a repayer, when in fact this borrower defaults. This is a false negative. And record 9, which the stump believes will default, when in fact it repays, a false positive. The total error for a stump is the sum of the weights of the incorrect samples. In this case, the total error is 0.167, that is to say 2/12 or 1/6. We use the total error to determine the voting weight that this stump has with the formula on your screen. Here the total error is represented by the value on the x-axis and the voting weight on the y-axis. The red line shows how the voting weight varies with total error. As the stump does a better and better job of classifying and the total error approaches 0, this stump gets more voting weight. For moderately low error values, here a value of 0.28, the stump will get less of a vote. Here it only gets a vote worth 0.5. Crucially, if the error is close to 1, that is to say we have a contrarian indicator, the stump gets a very large negative weight. This means we reverse the outcome of the classification and assign a high voting weight. We can plug in the total error for this stump, recall 0.167, and when we run the calculation or read off the chart, we see that this stump's voting weight is 0.8035. It's the sample weights for the incorrectly classified samples that determine the voting weight for each stump. We will now want to increase the sample weights of the 2 incorrectly classified samples so that the next stump's training data will be richer in these values and the next stump will be more sensitive to the errors that this stump made. We want to make it more likely that the incorrectly classified samples will be overrepresented in the training data for the next stump. These are the 2 records that were misclassified, record 2 and record 9. We will modify the sample weights using the formula on the screen. This means that the new sample weight is equal to the old sample weight multiplied by e raised to the power of the stump's voting weight. The orange chart shows how a sample weight of 1/12 would be modified by a range of voting weights. In this non-linear relationship, the higher the voting weight of the prior stump, the higher the new sample weight will be. For our samples, the new sample weight will more than double from the original 0.0833 to 0.1861. Now the flip side of this is that we need to decrease the sample weights where the classifier gave the correct answer. We do this in a kind of symmetric way with this formula. Note that the only difference is the sign of the exponent. This gives a different shaped curve with a higher voting weight associated with a lower new sample weight. When we plug in the old sample weight of 1/12 and the prior stump's voting weight of 0.8035 into the formula, or read the value from the chart, we see that the new weights of the correctly classified samples therefore reduce by over a half to 0.0373. We can record these new sample weights in our table. See that the values for records 2 and 9, recall these are the incorrectly classified data, are larger than for the other records. We'll need to normalise these weights so they all sum to 1. To do this, we simply divide by the total sample score, which in this case is 0.7452. This results in the normalised new weights you see in the table. We can then place these normalized weights into a cumulative distribution. Once this is done, it's a simple matter to generate a new bootstrapped dataset. We can pick a random number between 0 and 1 and choose the record that corresponds to that number in our cumulative distribution. For instance, if our random number was 0.04, we would choose record 1. If the random number was anywhere between 0.0501 and 0.2998, we would choose record 2. Observe, with this method, we are much more likely to choose either record 2 or 9 than any other variable. We can continue this method until we have our full slate of training data. This will be rich in the samples that we want, which were the misclassified records from the prior stump. We simply repeat this process hundreds or thousands of times, depending on the amount of stumps we need in our forest. We build a new stump from our new sample data. We see which split on which variable produces the best Gini impurity score. We calculate the voting weight of this stump and increase the sample weights for the records that were incorrectly classified by the stump and decrease the sample weights for the records correctly classified. This AdaBoost method is extremely powerful and results in ensembles with vastly improved accuracy over single classifiers. We've presented this technique using a random forest of stumps. Indeed, AdaBoost is very commonly used this way. But see, the AdaBoost technique is agnostic to the underlying machine learning model. You can use this technique with other ensemble classifiers such as k-nearest neighbours, support vector machines, logistic regression, or neural networks. Clearly, there's more compute time in training multiple models, and some techniques like neural networks are already very, very compute intensive. Nevertheless, the performance gains of using AdaBoost are always justified. This is Richard Walker from Lucidate. Many thanks for watching. In this video, we've seen one of the more recent innovations to AI and machine learning models, boosting. We've seen how we can use this technique to get our AI to focus on areas where it has trouble classifying and build a powerful, collaborative ensemble of diversified learners that cover each other's blind spots. Please join me in the next video where we will take a closer look at decision tree, random forest, and AdaBoost learners in action and compare their results.